Hello everyone, and welcome to another video of Do Math. Today we will be working on differentiating and integrating what's known as inverse trigonometry, or ArcTrig. So get your unit circles ready, let's jump into things. Okay, so the first problem here, a little bit of a differentiation practice problem. Find any x coordinates where the graph of the following function has local extrema. So we want to find the x coordinate where a local max or min happens, if there are any, and then identify whether it's a local max or whether it's a local min. So let's get started. We know that in order to find a local max or a local min, we need to find y prime, and we need to find where that is either equal to 0 or wherever y prime is undefined. So let's start by finding the derivative of y prime. So when I look at this, I see that there's a pretty clear inside here. I see that arctangent of x is my inside function, and the outside is simply something squared. So when I go to derive this, I'm going to use the chain rule. Let's take the derivative of the inside. So 1 over 1 plus x squared. So that's the derivative of arctangent. And then we multiply that by 2 times arctangent, so keeping the inside the same, and then to the 1 power. I technically didn't need to write that, but hey, there you go. So then our derivative is equal to, looks like 2 arctangent of x all over 1 plus x squared. So there's our derivative. Now what we want to do is we want to find where this derivative is equal to 0 or undefined. Now what I want to ask you is, do you know where or when a fraction like this is equal to 0 or undefined? Hopefully you do, because that'll make your life a lot easier. Whenever this fraction is equal to 0, that's going to be where the top is equal to 0. So if we want to find where our derivative is equal to 0 here, that's going to be equivalent to finding where the numerator is equal to 0. Because 0 divided by anything is still just 0. So I'm going to write that down just so we remember it. Let's take the top, 2 arctangent of x, and let's set it equal to 0 and see if that gives us anything. Now, as far as the undefined bit goes, think about this for a second. A function is undefined when the denominator is equal to 0, and hopefully, as you can probably guess, this denominator will never be equal to 0. X squared will always be positive, and then plus 1 will keep it positive. This will never be 0. So we don't have to worry about it. So let's go ahead with this over here then. Let's find where the top is equal to 0 to find where my derivative is equal to 0. So 2 times arctangent of x is equal to 0. That means that we are asking where is just plain old arctangent of x equal to 0. Okay, so remember, with arctangent or ArcTrig anything, the question that these are asking is essentially this right here. If we were to take the tangent of both sides, we would find that that's what x equals, because tangent undoes arctangent. As a matter of fact, I'm going to do that over here. Tangent of that side and tangent of that side will undo everything. So let's think about for a second what tangent of 0 is. Get your unit circles ready. Here's mine. 0 radians is right there, and that point I know is 1, 0. And I also know on the unit circle that tangent is equal to what? Yep, y over x. So that's what tangent is equal to at this place, at any place on the unit circle. So the y in this case is 0, and the x in this case is 1. So if tangent of 0 equals x, then that means x is 0 divided by 1, which means that x is just 0. So it looks like 0 is our critical point, and our only one at that. So let's figure out now what happens around this critical point. Let's make a little sign chart with y prime, and let's plop 0 on there, and I know that y prime is 0 at 0. I'm trying to find, is this a local max, or is it a local min? Or maybe it's neither. Let's take a look. So let's plug in a number that is before 0 into my derivative here. Now, remember, this bottom part will always be positive, so really all I have to do is figure out what will happen to the top when I plug a negative number in. Let's try plugging in something like -1. So if I plug -1 into arctangent, that's like asking tangent of what equals -1. Now, in this case, we can find where tangent is -1 by looking on the unit circle again. So on our unit circle, tangent is -1. It's going to be down here at -pi/4. So this means that the question mark here is pi/4. Tangent is -1 down here because this point is the square root of 2/2, comma, negative square root of 2/2. And if you do y/x for that, you get -1. So arctangent of -1 is negative because my question mark here is -pi/4. Now if I plug in another number on the other side, say 1, I get the opposite thing happening. Tangent is 1 up here at actually theta equals pi/4, because at this point I've got square root of 2/2, comma, square root of 2/2, and that's where arctangent is 1, at this angle, at pi/4. And because pi/4 is a positive number, I know that y prime will be positive. So that means that this point, this critical point, x equals 0, is actually a minimum, because y prime goes from negative to positive. Good reason. Okay, let's take a look at the next couple. So these all have to do with integration. Now before this, what I'd like you to do is look up the integration formulas that I've either given you in class or are in your book at the front of the section on integrating arc trigonometry. Take a look at those, and if you want, you can even give these two a shot. Okay, so let me write these down for you. I'm going to write down the two that I know we're going to need here, and coincidentally, the two that are the most common, and they are this. So the integral of, so du over square root of a squared minus u squared is equal to arc sine of u over a plus c. And the other one we'll be using is the integral of du over a squared plus u squared is equal to 1 over a times arctangent of u over a plus c. Like I've mentioned before, arcsecant, it is something to know, but it simply doesn't appear very often. It's highly, highly uncommon. These are probably the two best integration formulas to memorize if you wanted to go that route. So let's take a look at both of these problems. The first thing that I would do when looking at this first integral is to, well, think about what might be a good u. Now I'm looking at this 9x squared and this 4, and I'm looking at my formula right here at the u squared and the a squared. I'm looking back at the 9x squared, back at the u squared, and thinking, okay, I think I might know what a good u to pick here would be. And I actually think that a good u to pick would be u equals 3x. Because I know that if I do 3x squared, I'm going to get 9x squared, because 3 squared is 9 and x squared is x squared. And that would make my a, I'm just going to do this off to the side. In this case, my a would be 2. Okay, so let me rewrite this integral. I'm going to pull the 5 outside just to make things easier on myself. And we have 1 over, and then square root of 4 minus, and then u squared. I forgot to do one thing though. I didn't calculate what my what my dx would be equal to. So the derivative of 3x is 3, so my dx would be du divided by 3. So it looks like this integral would turn into 5/3. Integral 1 over square root of 4 minus u squared du. U substitution is really just pattern recognition. If you can make this pattern pop out, then 80% of the work is done for you. And that's what we've done right here. We simply made this pattern pop out in the integral that we're working with. We still had to do a U substitution, but this is how it worked out. Okay, and I know that according to my pattern, I can correctly integrate this as, all right, 5/3 arcsine of u over a. Now a in this case was 2 because 2 squared is 4. So I'm going to put u over 4 plus c. And that, my friends, is simply 5/3 arcsine of 3x over 4 plus c. There we go. Now let's take a look at the next integral here. If you'd like to give it a shot right now, you can. Okay, so what I'm going to recommend we do here is a little u substitution, where the u is going to be e to the x. Now let me be very clear about this. We're not going to do this e to the x. That's not what I'm doing. We're letting u be this e to the x right here. Because I know something that you guys might not see about this. And that's that if I rewrite this integral very slightly, I'm not doing u substitution yet, I'm just showing you something. I could rewrite it like this. E to the 2x is the same as e to the x squared. And that's something that I see, that's a pattern that I recognize, that once you learn to recognize, you can exploit over and over again in problems like this. E to the x has some very clever ways to hide exponent rules in it, and this is what we're doing. Okay, so let's proceed with the u substitution. If u is e to the x, then that means dx is equal to du divided by e to the x. And we can make our u substitution then here. There's no number to pull outside, so we just have e to the x over 1 plus. Now my u substitution was specifically focused on the bottom here, so it's e to the x over 1 plus u squared, and then my dx was du over e to the x. And as you can see, that cancels out this e to the x, leaving me with integral of 1 over 1 plus u squared du, which is very simply arctangent of u over a plus c. That's our arctangent pattern, so we can go right to integrating it. So we have got, let's see, 1 over a. A in this case is 1 because of that number right there. So I can just go right to the arctangent because 1 over 1 is 1. So that's arctangent of u plus c, again, a is equal to 1, and then that, if I go and sub things back in again, is arctangent of e to the x plus c. All right. Very nice. Okay, so looking at this problem, what we want to do is find the area of the shaded region. Now before you go, jump ahead and start this, what I actually recommend that you do is that you rewrite this as 1 over, and then we are going to rewrite this as 1 over 4 plus x squared minus 2x plus 1, just like that. And the reason for doing that I want you guys to be aware of is that this piece right there factors. So if you want to go ahead and try finding this shaded region right here, you're going to need to factor that as you integrate. If you want to, go ahead and give it a shot right now. Okay, so let's actually set up an integral to find this shaded region, 1 to 3 of 1 over 4 plus. Now I'm going to factor this thing right now, like I said would be a good idea. Let's take a look and see what it factors into. X squared minus 2x plus 1 is a perfect square. It should factor into x minus 1 squared, like this. And hopefully right now you see the reason why I did that. That's because this, right, should look a lot like our arctangent pattern from the previous page. So I'm thinking that maybe, just maybe, what we'll have to do is make this little integral pattern appear. du over a squared plus u squared equals, and then 1 over a arctan of u over a plus c, of course. So let's take a look and let's see if this actually happens that way. All right. If you hear that, that's just my cat throwing up a hairball in the background. Sorry about that. Now, let's pick a good u to substitute into this. So u equals x minus 1 would probably be a good u to pick. And then our dx would be equal to du divided by 1. So let's go in and make this u substitution. So 1 over 4 plus, and then we've got u squared, and our dx was equal to du over 1, which is just du. And then I can actually integrate this very easily because I know that with this 4 right there, my a is equal to 2, and that means that we can go right to this pattern right here. I know that with this integral pattern, I will get 1/2, because a is 2, arctangent of, and then u is x minus 1 divided by a, which is 2, plus c. And then we are letting this integrate from 1 all the way up to 3. All right, so let's go in and find the area then. So 1/2 arctangent of, all right, if I plug in 3 into this, so if I'm plugging 3 into my x right here, we would get 3 minus 1, which is 2, divided by 2, which is 1. So this is arctangent of 1 minus 1/2 arctangent of, and then 1 minus 2, 1 minus 1 divided by 2 is 0. So this becomes arctangent of 0. Now, being familiar with ArcTrig means that you're familiar with ways to evaluate them. Remember that ArcTrig is just backwards trig. So this arctangent of 1 is essentially asking at what angle is tangent equal to 1. And this one is asking at what angle is tangent equal to 0. So a quick little unit circle over here. Tangent, remember, is y over x. So in order for tangent to be 1, that means y has to be equal to x. And that actually happens right here at pi over 4. So this first division, this first part, will look like 1/2, and then arctangent of 1 is pi over 4 minus 1/2. Okay, and then tangent is equal to 0 whenever y is equal to 0, and that happens right here at theta equals 0. So I know then that the second part looks like 1/2. Then arctangent of 0 is just 0 radians. So this looks like 1/2 times pi over 4 minus, well, 0. So it's essentially just pi over 8. So this area is pi over 8. Okay, I know that ArcTrig can be a little bit confusing, but really what it comes down to, at least in calculus, is pattern recognition. If you can find these patterns in the integrals, if you can see those patterns in the derivatives, then you are one step ahead of where you need to be. That is the main idea of this. Okay, thanks guys, and I'll see you next time with L'Hôpital's rule.